this.
Okay.
This microphone's picking you up, and they're watching me there. If
Okay.
you want to walk
That's
around
not
too
my
much, we can.
presentation.
That's not your presentation.
No.
Sorry.
Okay.
I didn't load it this morning because I didn't
Think
think
I was
we
going
would
to
be
be
here,
here.
right?
I didn't think I was going to be here either.
We're glad you are. There we go. Okay. So backwards, forwards, microphone. If you want, unless you want this one.
No, this is good. Okay, my name's Steve Yokum. I'm going to discuss space hardware we have in ITC. Kind of follow on with what Matt just talked about here. Title's a little nebulous here, space hardware. What I'm really talking about is avionics hardware that's used in NASA space missions. So I'm going to talk about why we still need hardware in ITC, some of the resources we have in the JSTAR lab, and a couple of use cases, because more has happened since I wrote these slides, of how we have actually been employing the hardware in the JSTAR lab. So the need to maintain the hardware. So software models, like Matt just talked about, they provide a tremendous benefit. Uh, we literally take the software binaries as is, we don't touch them, and we can execute them right in these software-only models of the hardware. They're functionally equivalent because it is the software. And a big benefit of these is they're portable and shareable. We can, if somebody has a Dell equivalent laptop or PC, they can run a whole spacecraft. So you can share these out with hundreds of people. If you think about a hardware in the loop simulation of JWST, for example, costs millions of dollars to build it, months to put it together, and you couldn't think of sharing that out with hundreds of people. Within Northrop alone, they're struggling to deal with the lack of hardware. So that's the great thing about software models, and that's definitely a direction we still want to be pushing forward. But there obviously are still some limitations with the software-only models. Some of those being timing, performance, and the accuracy of the software model under anomaly and exception conditions. Timing. Timing is a very complex bug you can get into a system. It may not reproduce predictably. It can be very inconsistent. It can take days and days before you can get it to reproduce. And often this is a result of very complex interactions with multiple threads. Often the developers of the software themselves don't even understand how all these parts play together. So that can be one of the more difficult bugs, unfortunately, you can flush out of a system. And a software-only model a lot of times can't reproduce that very accurately. And I'm going to go into now why that is with timing. So if you look at what the software-only simulation is doing, it's modeling a whole bunch of components within one host CPU. So I'm going to use James Webb as an example here a lot, but so if we look at like James Webb, we're modeling ISIM CPU, the SBC flight control computer CPU, the 1553 controller, the spacewire controller. All that's getting modeled on basically your Intel processor. Each of these components, CPU, the North Bridge, the South Bridge, your LAN, 1553, those are all a clocking chipset. One host CPU that's modeling this can't run all that simultaneously. It can only run one at a time. Each of those has to be scheduled. So what that does to asynchronous events like interrupts is they may not happen as they would on the real hardware. For an example, if normally in the hardware, if the spacewire chip is going to generate an interrupt, and then always the 1553 is going to generate the next interrupt, if you were to schedule in software the 1553 one first and then the spacewire, potentially those could come in out of order from what they would nominally in the hardware. Other things are latency and jitter. If, for example, you're taking your instructions out of EEPROM and running them, that's going to take some amount of latency. If you're running them directly out of RAM, that's going to take a different but less amount of latency. These are things that are very difficult to recreate in software. So these subtleties generally aren't important. They don't affect a lot of the functional capabilities, but every now and then they do hit you, and they can hit you bad. Performance. This is probably one of the lesser of the problems, but uh, running these in real time can be difficult, and that is because, again, we're running assembly instructions. That's what we're getting from these flight binaries. We're pulling out the assembly instructions and running them, but we have to do that for every single chipset that's in the model. So we have to run ISIM CPU, we got to run spacecraft CPU, we've got to run the 1553 clocking CPU. All this has to be run in parallel in one host CPU that, is also got whatever that host operating system is doing and everything else. So getting up to real time can often be difficult. Now, that really doesn't matter a lot of times if you're the master clock and you're simulating every component. So you can run faster in real time, slower than real time, and that's often desirable. Doesn't make a lot of difference. But if you bring in external components like a ground station, let's take Eclipse for example, we're not controlling Eclipse's clock. So if it's sending up a command and it's expecting back a response in 2 seconds, and we're running 4 seconds below real time, the whole thing's broke right there. So those are cases where we have to get this thing up to real time to get it to work as a full integrated system. Accuracy. And here again is a big problem we've been running into lately with the software-only models. So this is a big undertaking if you aren't very familiar with it. And I just came on in March, and I didn't really have a good concept of what ITC was doing here. And I was like, wow, this is a really big undertaking. You're looking at a lot of complex hardware features that a lot of software guys you don't learn these things typically in an undergraduate computer science or computer engineering class a lot of times. Interrupts, DMA, registers, memory maps, exceptions, interactions of multiple components, timings, all these things have to be recreated in software. And the problems we get hit with is to do that, you have to have a specification of the hardware in its full-blown glory. If you don't have all of that, you can't completely recreate that piece of hardware in software. You rarely get it all. And in some cases, we have to look at the software and see how it interacts with the hardware and recreate the hardware model that way. Well, obviously there's going to be some inherent things missing there because the software, we're only looking at what the aspect of the software that it's using to the hardware. So we've obviously missed modeling some of the hardware right there. Due to the sheer complexity of this, it's easy to get the nominal paths working, but then a lot of the exceptions and anomalies get left out. The machine checks, the instruction interruption instructions, the data checks, a lot of times those don't get properly modeled because you're not hitting those unless the software is crashing. So, those typically don't get a lot of attention. Another example, and this isn't the only example, is let's take analog, for example. If in a real system, analog is going to always have some degree of noise coming in. So in the software model, there is no noise. Everything comes in perfect. Believe it or not, that can create problems because it is perfect. So in specialized cases, this can make recreating errors impossible. So that's kind of an overview of why we still have to do some of the hardware. I'm going to go into what we have in the JSTAR lab and what we use as far as hardware to overcome some of these deficiencies in the software model. So the big thing is the RAD 750. Obviously, this is kind of the de facto COTS board, if you will, for NASA missions. There's kind of two standards for the RAD 750, the 3U and the 6U. There's some variants within that, but that's the two big trees of the RAD 750, or the 6U and 3U size single board computers. So the one we have has no integrated I/O, but we do have 1553 SpaceWire Ethernet on the compact PCI backplane. The 6U model we have has integrated 1553 and SpaceWire. I'm told it's the exact same model that happens to be an LRO. Just to show here that, a lot of these missions are using the RAD 750, and that's why we put a lot of emphasis into that particular piece of hardware, because it seems to be where most of the missions are going. If they're not using a custom piece of hardware, it looks like they're using the RAD 750. It has been well proven to be radiation hardened in space. In addition to that, we do have 1553 and SpaceWire tool sets. We can be RTs, BCs, SpaceWire routers, SpaceWire nodes. So we can do those type of things in hardware to emulate those I/O interfaces. Again, 1553 and SpaceWire tend to be the two de facto communication standards for most of the space missions, at least that I've seen to date. So some of the things that we could do for the facility with the 750s, we can execute the full VxWorks and RTIMS operating systems. We have done both of those, and we've done VxWorks 5, VxWorks 6.4, and ran RTIMS. So any of the interactions we want to see with the operating systems and the hardware, we can do that. We can't take full flight binaries and put them on the RAD 750 just because everybody has some customizations to their system. So that's impossible, but we can take sections of flight code and target them and recompile those sections and target them for the 750. We're also building up some capabilities now to interface the software simulations and run modules over the 1553 bus on the actual hardware. So we'd have the software and the hardware running jointly together, which is just another tool in the toolbox for doing different types of testing in V&V. Okay, now I'm going to go into kind of some of the use cases we've been hit with and where we have immediately had to go to the hardware to do this verification. The software-only models didn't work out. I'm going to discuss two here. One of the initial ones here was a Juno anomaly we were given. So there was a condition where a interrupt instruction was being raised in the processor. Okay, not a huge deal, but there was really a weird thing going on with this, and it's that what should happen is that exception should occur, task should suspend, and that's it. But what was happening here was the exception was being raised, and then the task was continuing to run, and then the exception was being raised again. And this kept happening over and over at 10 hertz until finally a higher level monitor task caught this, and it made the whole system do a cold boot, and it switched over to the other side, which is really undesirable. If it just would have interrupted, the system would have done a warm restart, and they could have captured a lot more in RAM what would have happened during a downlink. So it was really a strange occurrence that happened. So JPL asked that IV&V kind of look into this and see what we could figure out. So we took this to the software model and immediately found out that we couldn't get anywhere with that. The ISI just wouldn't show up the same. This wasn't working out. So we moved a VxWorks 6.4 image, which is what they run on Juno, and took it to the RAD 750 with a little test driver to see if we could get some of this same behavior to occur. We were given a hint that this was maybe happening in the VxWorks task control block, and what we were able to do is find the exact bits in VxWorks task control block that you could go in and manipulate, and lo and behold, we could get this exact same behavior to reoccur on our RAD 750. So we gave this information back to JPL and Lockheed, and to help them with their analysis of this anomaly. So unfortunately, there's not like some super happy ending here where it solved the mission. eventually this was just determined, well, this was a fluke and we're not even going to end up doing anything with it. But the important thing to note here was we were asked to do this by JPL and the contractor, and we were, through the use of our hardware in-house, able to reproduce this anomaly and say, here is the exact bits in the operating system that would have caused this exact behavior to happen. Additionally, just recently, there's another NASA mission that Dan Painter came to us and said, hey, look, I've got this behavior I need you to look at. I got the RAD 750 cache and how it's moving that memory from CPU cache to RAM. I need some analysis on that of what's happening there. Well, I didn't even need to go to the software model here to know it wasn't going to happen. CPU cache, on the Power PC, nobody really knows what's going on there. That's all on the CPU's transistors. It's doing that logic. I knew the software wasn't going to even attempt to model that. So again, we went into the hardware and we were able to do the analysis he wanted to see what the behavior was and the timings of moving data from the CPU cache back to RAM and how that behaved. So in conclusion, obviously there are many tools in doing successful software IV&V. Static analysis, obviously that's a huge one here. What ITC brings is dynamic analysis with the software models. That's a huge player as well. However, there are always going to be cases where flight equivalent hardware is needed to verify some of these specific anomalies that you're not going to catch through static analysis or through the dynamic analysis of software models. And that's the same slide that Matt showed you. So Justin Morris is kind of our task lead, and if you need us to provide any more examples or modeling on hardware or demonstrations, we'd certainly be happy to do that. Questions?
Curious about the solution to that spurious ISI interrupt problem. Couldn't they have reprogrammed the boot code to ignore that, and so that it wouldn't boot up after a certain number of occurrences of that? I mean, that wasn't a solution, obviously. Otherwise, they would have done that.
Well,
because they ignored it.
Yeah, keep in mind they don't know they never did figure out why the first ISI ever triggered. So that never got figured out. What did happen was once it triggered, it broke some piece of memory, the piece that we found here, that caused the operating system to get in that strange state. So without ever knowing the root cause, I don't think they wanted to take the risk of going and reprogramming the spacecraft. Sam Brown, if he's here, maybe could tell you, I guess he's not, can maybe tell you more about that. But I think that was deemed too high a risk to reprogram the spacecraft when it was in flight without really knowing the root cause of the anomaly.
I guess it didn't happen very often to be a real concern then.
Well, it only happened once, and I think
okay.
I think they concluded this must have just been some fluke radiation, and we're just going to take that risk and go forward.
Right. Okay. Thanks.
I'm Pat Olguin. I'm definitely not a hardware guy. So when you guys are emulating hardware, chipsets and so on, are you able to dynamically, and I mean just like, using either like parameters or adaptation data, the manufacturer's errata sheets, because they have known problems. Are you able to incorporate that, or you just have to go straight from their original specs?
Yeah, we have to. It's a difficult process. I mean, we use errata sheets, we use the original specs, and we find errors in those. So we'll hit cases where the flight software we get doesn't run, and so where do you go from there? Is it a bug in the flight software, or is it a bug in the model you created that hardware because you got a bad errata or spec sheet or whatever? And you have to do a lot of analysis sometimes to get all that traced down to figure out where the root cause of that was. A lot of times it is in the spec that was just wrong. That happens frequently.
I know in Sam Brown's case, they were able to feed back, information to to BAE for the RAD 750K. I mean, so I know that's a pretty big impact when you actually go back to the hardware developer and say, you know what, you have a design flaw here, and they have to fix it. Another question is, are you guys using any off-the-shelf emulators?
We use Symix is a big one we use. That's kind of our main engine we use for the execution of the assembly code is a product from Wind River called Symix, and that's the one doing all the models that Matt talked about. We're also using a open source one called Kimu. We're looking to build up that capability mainly because Symix has a complex and expensive licensing strategy where Kimu is all free. So if we could get away from the licenses, it would make this distribution to our users even easier.
And one more thing, you guys, I may have missed it in the first presentation. Do you guys have any remote capability? In other words, for remote users?
Yes, we have. We call it vCloud, and you can connect to any of our simulations remotely from, I suppose, anywhere over the internet to the JSTAR lab and run, just the JWST simulation or the other ones remotely over the internet. So there's no location constraints to running the full spacecraft.
All right, thanks.
Curious, Steve. The first one, I'm just curious. When we do you turn on a computer and it goes on its power on self-test or any type of built-in test or anything like that. For the software models, do you typically ignore that, startup time, for these processors? Do they just ignore that step, or?
You mean the time to get from? Well, are you referring to time to where you hit the first assembly code, or? I mean, I think when you power on, you're going to hit an assembly instruction immediately. Then you're going to go off and probably request a bit test, and then there's a time lapse there. Yeah, typically those time lapse are things that get ignored, so that we just blow through that and get right up to the main application level. Okay. If we find reasons, and we have found reasons why those times matter, then we have to go back and model those things more closely. 95% of the time, those timings don't really matter for what we're trying to do, so we don't want to spend our labor efforts really focusing there. We want to get into the application software and focus our efforts testing there. But yes, there are times when we have to go back and focus on those times.
Second question was relative to the first limitation you brought up about timing and whatnot.
Mm-hmm.
You have multiple things loaded on the board, and so of course that's burdening that one CPU.
Right.
Not to negate the need for hardware in the lab, I'm curious your first reaction to farming these things out that you're modeling to multiple different processors or different cores.
Mm-hmm.
If you see any advantage with the new boards that are coming out with more cores than just single cores running these applications, do you see any? Wow, that might be some advantages.
Yeah, I think if you got this thing multi-core distributed, so that you would put, for example, iSIM CPU on a core of your Intel and SPCs on a core, you could get huge advantages. We just don't have the underlying support from that in our simulation tools to completely get there yet, but that's a goal to certainly do that, because that would make a huge difference. In 10 years, probably a lot of what I just said here is going to be irrelevant, because it is going to be flushed out by more advanced multi-core chipsets and more advanced software emulators of the hardware.
Just a quick comment. I'm glad you brought up that real-time issue, because we've seen it as well, and it's actually something in our system risk assessment. We're now working in, is it interface, what's the integration like on our equipment, because we have seen those types of issues.
Oh, okay. On what particular?
on the engineering and scientific instrument equipment running in real time, and we have different systems may be interfaced differently. We have secure data repositories hooked in. We might have what's called a LIMS, a laboratory information management system, runs back into a database as well. We have a couple different, we have some web technologies as well. So depending on what that is, it may be interfaced differently or even integrated differently. Some of the data might even come out into a translational Excel tool and then get picked up by a data repository. So a couple different scenarios going on there. So when we're evaluating the equipment, we also have equipment that might be a standalone R&D instrument.
Right.
In that instance, we don't have any of the
Right, you
complexities.
can't control its clock, so you've got to be in step with it.
So that's why I said I'm glad you brought it up, because Ryan and I said, well, that's why we have it in our risk assessment.
Yeah, definitely.
I don't actually have any questions online, so we'll take a 10-minute break and return at 2:30.